Hello. Today we're going to talk about a way to increase the performance of CPU dramatically. Um, it's going to require a redesign of the CPU, but it's going to be worth it. Take my word for it. So here we see the typical block diagram for the CPU that we have been dealing with in class and in lab. And as you know, the sequence of events is we fetch an instruction and we put it in the instruction register. Then the outputs of the instruction register are decoded by the decode logic, which drives all the control signals to the hardware. If we're going to fetch any values out of the register file, then we have to do that. And then eventually the inputs to the ALU are present, and the ALU will produce an output which might require addressing memory, getting a value back, or putting a value in for that matter, or just saving the result of the ALU. Then, while that's been going on, of course, the next address to be fetched has been calculated. However, it might be a conditional instruction, and so we can't really know what the next address is until the ALU has finished. We get the condition codes out, and we can then make a decision about whether to branch or not. So we've got all of these things that are happening. But look at this. While the ALU, not the ALU, while the register file is finding the operands and producing them at the output, while that's going on, we're not really using the decode logic anymore. It's already done its job. We're not really using the instruction register anymore. It's done its job. Now, since the decode logic is combinational, we can't really change the value in the instruction register because that would change inputs to the decode logic. But if we could capture the value in the instruction register, we could continue to feed the decode logic, and it could continue to feed all of these signals, and the instruction register would then be free. What I'm basically getting down to is at any moment in time, there's usually only a small percentage of the components in this CPU that are actually doing anything useful. Now, most of the components are doing something, but they're not doing anything that contributes to our instructions. So at the beginning, the instruction register and the instruction memory are the only ones doing any useful. Then we latch the instruction register. Now it's the decode logic that's doing something useful. And we've got propagation delay through there. And then as soon as that those control signals come out, then we've got propagation through the register file. And when that's over, we've got propagation delay through the ALU. And when that's done, we load the value, the result, back into the register file. We can break the execution of an instruction up into these steps. So we want to look at this over several clock cycles. So these are clock cycles. And up here, we're going to look at the stages that each instruction has to pass through. So here we have instruction fetch, and then we have decode, and then we have execute, and then we have memory, and finally we have This is where we store the results. We call that write back. Okay, so when clock cycle 0 occurs, we're going to fetch instruction A. When the next clock cycle occurs, we're going to move instruction A over to the decode stage. Now, because we've redesigned the CPU and the hardware for each of those stages is independent, as soon as instruction A moves over to the decode phase, that means the hardware associated with instruction fetch is no longer used. So we can use it to fetch another instruction. Then the next time a clock cycle occurs, instruction A is going to move over here to the execute stage. Instruction B will move to the decode stage, and we will fetch instruction C. Then the next clock cycle, A goes to memory, B goes to execute, C goes to decode, and we fetch instruction D. Then on the next clock cycle, A moves over here to write back, B moves to memory, C moves to execute, D moves to decode, and we fetch E. On the next clock cycle, A has now completely executed all 5 of the stages. So A disappears. And we fetch F, E moves over here, D moves over here, C moves over here, B moves over here. Then we fetch G. F moves here, E moves here, D moves here, C moves here, and B has gone because it's been completed. We fetch H, G moves here, F, E, D. So you see, in order to completely execute 4 instructions, we needed 8 clock cycles. Don't forget, we're starting with 0 here, so there's 8 clock cycles. Now, that doesn't seem very efficient, since we could execute 1 instruction per clock cycle. But suppose that each of these instructions can move through a cycle a lot faster than they could in the original design. That means we can make these clocks faster. So how are we going to redesign the CPU in such a way that the hardware necessary for each of these phases is independent of the hardware for other phases? We know that in the first stage, we're going to need the instruction memory, we're going to need the program counter, we're going to need the instruction register. So we move over here and we put all of this together. This is the program counter, exactly what we had before. Here's the instruction memory. Now I'm putting the instruction memory here. It's physically not going to be part of the CPU. It's still external to the CPU, but it makes this diagram a lot cleaner if I put it right here. This is the adder that computes the next sequential address. This is the adder that computes the return address for function calls. And then this is the data that comes out of the instruction memory, and that makes it the next instruction to be executed. Okay? What is this? Well, this is a new component that we're going to add in order to isolate this hardware from whatever comes next. This is a register. It's called an interstage register because it's the register between stage 1 and stage 2. It can be a very large register, as you will see pretty soon. See, this is a 32-bit output right here. This is, however big your instruction memory is, which is 32-bit in our case. This is also 32 bits. So right here, we've got, what, 96 bits that we need to hold these three values. And there may be more. But you see, this is all that we need to fetch the next instruction. We just need to know an address, and we're going to get that address from here. So this is for sequential address instruction. We may change some things later. All right, now for stage 2, you see stage 2 needs to know what the next sequential address is. It also needs to know what the return address is, and it needs to know what the instruction is. But with those 3 pieces of information, stage 2 can do its job. And those 3 pieces of information are latched into this register by the system clock. And as soon as they're latched in here, we don't need this adder to be working on anything for us anymore, not for this instruction. We don't need anything from the instruction memory for this instruction, and we don't need anything out of this adder, as we captured everything we needed. Now, don't forget that the data coming out of the instruction memory is the instruction. So since we're going to latch that in this register, or a portion of this register, that makes the portion of this register that holds it equivalent to our instruction register. Notice there's no instruction register over here. This will count as the instruction register. And from this, we can get the RS field, we can get the RT field, we can get the RD field. Now, we don't need the RD field in this stage of execution, but we are going to need it later on. So we're just going to pass that on to another register, which isolates stage 2 hardware from stage 3 hardware. We're going to need RD later on, so we just pass it on through. The immediate field of the instruction is the least significant 16 bits. We may need that if this is an immediate kind of instruction. We can sign extend it, either signed or unsigned, same hardware we had before. Now, this is the next sequential address, and we can take that. Remember, we strip off the most significant 4 bits, and we combine that, we append that with the target value. That's the least significant 26 bits, and we shift that. That gives us 28 bits. We add the 4 bits from the next sequential address, and we're back to 32. This is the absolute address. If the instruction that is filling or occupying the decode stage, if that instruction happens to be a jump instruction, then we're going to need the absolute address later on. If it is a relative branch instruction, then we're going to need the next sequential address so we can add something to it. If it's going to be an immediate instruction, we're going to need the immediate value, either shifted or not shifted. Going to need that later. We're going to need possibly the RT field later. And we're certainly going to need the 2 output values from the register file. So each stage really has 2 goals. The first goal, of course, is to actually compute whatever is supposed to be computed in that stage, and in this stage it's the decode logic. But we also have the responsibility of moving items forward from the previous stage, even if we are not going to need them, but we know other stages will. So this is where we decode and fetch the operands. All right, next, we have the execution phase in stage 3. Now, in stage 3, we will compute a relative address, if that's what we need. We're going to carry RD and RT forward. But here is where the ALU computes its value. All of these components were part of the original design. All we've done is add these registers. And we got rid of the instruction register, so we saved a little bit of hardware there, but these are pretty good sized registers. And so everything that we need from this stage moves on and gets stored in this interstage register. Now if we go on to stage 4, that's the memory stage. That's where if we have to read or write memory, this is when it happens. And notice that the possible next instruction addresses come over here, and I'm going to put that MUX in that we have always had in our design, but I didn't put it in the design of stage 1 just to make it simpler, but now we have to put it back in. This is the MUX that chooses which address the program counter is going to supply to the instruction memory. And then also, if this is a data access, that's where we do the data access. The rat's nest does its thing. And now we're going to store, what are we storing here? We've got RD, we've got RT. This is the condition codes. This guy is the result of the ALU. This is the rat's nest if we're reading from memory. If we're writing to memory, then it gets taken care of in this stage. If we're reading from memory, the value that we read comes out and gets stored over here. And this is the return address that we've just been passing along all this time. And then the last stage is called write back. This is where we choose we choose what register is going to receive the result. We actually supply the result either from memory or from the return address here or from the ALU. This all assumes that we're actually going to write something. A lot of operations don't write. And it also provides the branch information necessary to choose which one of these gets passed on to the program counter. And so this is basically the entire CPU, only it's now been pipelined. Can't highlight that very well on a PDF file, but this is called pipelined. So one instruction is being fetched, another instruction is being decoded and having its operands fetched. Then the next instruction executes, that is the ALU. The phase after that is memory, and each of these are different instructions, and then we have write back. Now, there are a couple of things to notice here. First of all, when we write back into the register file, if this is instruction A that's going to do write back, instruction B is accessing memory, instruction C is in the ALU, instruction D is having its operands fetched. And at the same time, instruction A wants to write its results back to the register file. But that's okay, because if you remember in the register file, we can be reading two registers while we write a third register, and it can all happen independently. And in this case, the thing that we're writing isn't even part of the same instruction that we're reading. But again, that's okay. We are not going to be interfering with each other. Now let me give you an example of what might happen. Suppose that instruction A is going to write a new value in the register 5. And suppose instruction B needs to use that value in register 5 in order to continue its execution. Well, the actual value that instruction B will see in the register file is incorrect, because it is not the value that instruction A will put there. You see, instruction B, these instructions do not know they're being pipelined, and so instruction A wants to write something back into the register file, but it can't do it for 5 clock cycles until it gets over here. But instruction B wants to use that value now, and it can't. That is a problem. That is called a data stall. The pipeline doesn't really stall because we want to continue instruction A until it gets complete, because we're waiting on it. So what happens is, on the first clock cycle, instruction A is fetched, comes over here. On the second clock cycle, instruction B is fetched. Instruction A gets decoded and its operands are found. Then instruction A moves over here. Instruction B moves over here. Now, as soon as instruction B gets over here, we realize that instruction B needs register 5, but instruction A hasn't supplied it. So instruction B cannot move on, so it stalls right here. On the next clock cycle, instruction A is going to move over here, but instruction B is not going to move over here. That's called a bubble in the pipeline. So this stage of the pipe is not being used. Then the next clock cycle comes along. Instruction A moves over here. The bubble, I guess you can say it moves over here, but since B still can't move on, another bubble appears here. So now we've got 2 stages that aren't doing anything for us. Now, at the end of that clock cycle, instruction A does write its results back here. So now instruction B can continue, and instruction B moves on. But that is a data stall, or a data hazard is another term for it. And you want to avoid data hazards as much as possible because they make the pipeline inefficient. These bubbles represent hardware that's not being utilized. Our whole goal here is to keep all of the hardware in the entire CPU busy all the time. Now, sometimes you cannot actually do that for a variety of reasons. The situation that I just described, a data hazard, might be solved or prevented by rearranging the order of the instructions in your instruction string. For instance, might it be possible to put a couple of instructions in between A and B? These are instructions that do not rely on whatever A and B are doing. But that would give A time to get over here and supply the value before B needed it. That's called out of order instruction. A lot of compilers and assemblers that do know about pipelining, they may go in and they may, without your knowledge, rearrange the instructions in your program to get rid of data hazards. There are also other kinds of hazards. For instance, if you're going to do a jump instruction, and let's say it's a conditional jump instruction, a branch, well, you won't know the condition until after you get over here. Well, the way conditional instructions work is we're either going to branch or we're going to execute the next instruction. We certainly can prefetch the next instruction. There's a chance we won't use it though. Most pipelines will prefetch the next instruction on the hope that it's going to be the correct address. Now, when we get down here and we actually find out what the condition was, then that may not be true, and we will have to replace it, which means that the instruction after the branch won't be used because we're going to branch. Well, it's in here somewhere. We need to clear out whatever it's done, need to clear out whatever the instruction after it is done, and whatever the instruction after it is done, and we are now fetching the correct instruction for the branch. But there's a bubble here, there's a bubble here, and there's a bubble here. And so it takes a while for the pipe to fill from that new instruction. Pipelines make the hardware much more efficient under certain conditions. And the conditions are that we can make this hardware run much, much faster than the overall CPU could. Because if we cannot make this run faster, then this is actually slowing us down. If we're using the same clock speed here that we were using in the original CPU, then we've made it 5 times slower, essentially. What we need to do is we need to divide the hardware up such that the propagation delay through each section of hardware is approximately the same. And we would like it to be, this is a 5-stage pipeline, so we would like the clock to be at least 5 times faster. If we can make the clock 5 times faster in a 5-stage pipeline CPU, that's 5 times faster than the non-pipeline CPU. If we can make our redesign sufficiently fast that we can clock it 5 times faster than we did the whole thing, then we haven't lost any time. But if we can clock it 7, 8, 9, 10 times faster than we were, then we're actually executing instructions faster than we were before. When the pipeline is full, it appears to an observer that 1 instruction per cycle is being executed. Now, that's not exactly true. Think of this as an assembly line. This is a Chevy assembly line in Detroit, and you're standing here at the door where the completed vehicles roll out, and you've got a stopwatch. And you time how long it takes in between each car coming out. And let's say a car comes out every 2 minutes. Well, your first inclination is to say, it takes 2 minutes to build a car. Well, you know that's not right. But Each of these stages allow the car to be built little bit at a time. And what you are measuring is how long it takes for that last stage to work on that car. If you want to know how long it takes to build a car, then you need to mark I don't know what you would mark coming into the assembly line. Mark, put a mark on the hood or something, and measure how long it takes that to go all the way through. That's how long it takes to build a car. Another way would be to know how many stages there are, and you just measured how long it takes for one stage. And so the total execution time of an instruction is how long it stays in each stage times how many stages there are. And that's the whole goal here. Keep the hardware busy. That will speed up the instructions. And one of the reasons that we can increase the clock speed to these registers is the propagation delay for each of these stages is running in parallel now. Whereas before, we had to have those propagation delays all calculated into the clock cycle for a single clock cycle. The clock cycle had to be long enough for all those propagation delays added together to work out. Now, the clock cycle only has to be fast enough to allow the propagation delay for the slowest stage. So we can crank up the speed, and that's how we do pipelining.